In this video, we introduce an important technique in geometric measure theory called tangent measures, which were introduced by David Price in a paper in 1987 and have been used not just for studying geometric measure theory, but also in other fields like PDEs and dynamical systems. So recall that for smooth manifolds, at any point along a manifold, if I start zooming in at that point, then my manifold begins to look more and more like a n-dimensional plane, which we call the tangent plane. So here, for example, I have a smooth curve, and I've highlighted a ball center on the curve and then blown up the image of my surface of my curve inside that ball to the unit ball on the right. So notice that if I take the smaller and smaller balls and I blow up the image, or that is to say, if I zoom in on my curve in smaller and smaller balls, you'll notice that the curve is getting flatter and flatter and looking more and more like a line. Now, instead of zooming in on a curve or a surface, I start zooming in on a measure and looking at the resulting measure that I see as I zoom in smaller balls. There's no theorem that says that this is always going to converge to some measure. However, at almost every point in the support of my measure, if I zoom in at least for a certain sequence of radii, then I can guarantee that these sequence of zooms or these sequence of blowups will converge weakly to another measure. So let's try and be more specific about what we mean by blowing up a measure or zooming in on a measure. So let's suppose we have a radon measure mu, and we have a point A in Euclidean space and some positive radius r. We define T sub AR to be equal to x minus A divided by r. So this is the map that takes the ball center at A of radius r onto the unit ball bijectively. And observe that if we look at the push forward of measure mu under this map TAR, then the push forward measure of a set A is the same as mu of r times A plus little a. So let's visualize what's going on. So suppose we have a measure mu whose support is equal to some curve gamma that we've denoted in blue. And suppose we have a ball BAR centered on the curve gamma. So what the map TAR does is it maps Euclidean space back onto itself so that the ball BAR gets enlarged to the unit ball B01. By doing so, it enlarges the portion of gamma in the ball BAR to the unit ball. So you can think of the unit ball in this case like the lens of a microscope through which we are looking at the ball BAR through this lens. So the push forward measure of mu under this map will also have its support translated and scaled up to unit ball, and the support of the push forward measure will equal the blown up version of gamma. That is the image of gamma under this map. Notice that even though we've translated and enlarged the support of the measure under this transformation, the measure of the ball has not changed. That is, the push forward measure of the unit ball is equal to the original measure of the ball BAR. We say that a non-zero radon measure nu is a tangent measure of a measure mu at a point A in Euclidean space if there are a sequence of constants, positive constants ci and radii going to 0, so that ci times the blown up versions of mu at A with respect to the radius ri converge weakly to the measure nu. And we denote the set of all tangent measures of mu at the point A by tan mu of A. So let's take a look at a few examples. So first, suppose that mu is a linear combination of Dirac masses centered at a discrete set of points, where by discrete I mean that the set has no accumulation points. Then you can show that for mu almost every x, the set of tangent measures at x will be all positive multiples of the Dirac mass centered at 0. So notice that the Dirac masses are centered at 0 and not any other point, because remember that the map TAR used in the definition of tangent measures recenters balls to the origin. Now, if gamma is an image of the unit interval under a Lipschitz map, then if we look at Hausdorff measure restricted to the curve, we'll see in later weeks that the set of tangent measures at almost every point is going to equal just all positive multiples of Hausdorff measure restricted to some particular line. Finally, if we have a set A of positive Lebesgue measure in RD, then the set of tangent measures at almost every point in A of the measure of Hausdorff measure restricted to the set is actually just going to equal all positive multiples of Hausdorff measure. In fact, what we'll show is that if you look at r to the minus d TAR push forward of Hausdorff measure restricted to the set A, that this converges weakly to Hausdorff measure on Euclidean space for almost every a, little a and big A. So this isn't exactly the same thing as saying that all tangent measures are going to equal a multiple of Hausdorff measure. But later on, we'll see a result that says for measures such as Hausdorff measure restricted to a set of positive Lebesgue measure, that in fact all tangent measures can be obtained in this way. Okay, so we'll give a simplified proof of this fact. So we need to show this weak limit. So we need to show that this measure integrated against any continuous function of compact support converges to the integral of this function against the same continuous function of compact support. Without loss generality and for simplicity, we're going to assume that the support of our continuous function is inside the unit ball. Okay, now we're going to let A be a Lebesgue density point of the set big A. Okay, so now if we look at the integral of phi against our measure here, okay, now recall since we're taking push forwards, this is exactly the same thing as just taking the integral of phi composed with TAR, which is x minus a over r, times the original measure, or integrated with respect to the original measure. Okay, now we're going to split this integral up. So notice that this integral up here, so this is the same thing as taking the integral of phi x minus a over r times the characteristic function of a. And we can write just the characteristic function of all of Euclidean space as equaling the sum of the characteristic function of a plus the characteristic function of a complement. So thus, this means that the characteristic function of a is equal to just 1 minus the characteristic function of a complement. And that allows us to split the integral into this sum, where we have the integral of phi with respect to Hausdorff measure, plus the integral of phi times the characteristic function of a complement with respect to Hausdorff measure. Now we observe two things. One is that by a change of variables, you can actually show that this integral is just equal to the integral of phi against Hausdorff measure. And then over here, notice that because phi is supported inside the unit ball, that means that this function will be supported inside the ball centered at A of radius r. So thus, that means that this is going to be at most so really I should have the L infinity norm of phi here times the characteristic function of BAR times the characteristic function of a complement times r to the minus d. Okay, but r to the minus d is comparable to the Lebesgue measure of the ball BAR. So actually all of this is at most a constant times the average integral over BAR of the characteristic function of a complement. And because we've picked the A to be a density point of the set big A, that means that this integral as r goes to 0 will actually go to 0. So this integral goes to 0, and thus what we have remaining is the integral of phi with respect to Hausdorff measure, which since this holds for every phi, that implies weak convergence to Hausdorff measure. Now, tangent measures don't need to actually exist everywhere in the support of a measure. So here I've given an example of a measure mu so that 0 is in the support of the measure and the set of tangent measures of mu at 0 is empty. So I'll leave it as an exercise to verify that this is the case, but the key idea is that no matter what sequence of points Ci that you pick, and no matter what set of radii Ri you pick, if you look at the sequence of blow-ups, which we'll call mu I, if you pick these Ci and Ri in such a way that there happens to be a ball centered at 0 of radius r, where the measure is not going to 0, so let's say it stays at least some constant c bigger than 0 for all I, then you can show that this implies that the ball centered at 0 of radius 2r must go to infinity. And so thus there's no way that this sequence of measures can converge weakly to a radon measure, which in particular has to be locally finite. So recall that in the case of the manifold, the set of tangent planes at a point is unique. There's only one tangent plane. And in particular, you can show that the set of tangent measures at a point, at any point of a smooth manifold, are unique up to constant multiple. They're all multiples of Lebesgue measure restricted to the tangent plane. Now, this isn't the case in general. So for general radon measures, it's usually not the case that there is only one tangent measure up to constant multiple. Usually, they are not unique. And in fact, there is an example of a radon measure, so at almost every point in its support, the set of tangent measures is actually all radon measures, which is crazy when you think about it, because let's say we came up with a measure that was a function times Lebesgue measure, where the function took on values between 0 and 1 in the plane, whose values corresponded to the grayscale image of the Mona Lisa. Then at every point in the support of this measure, if you look down far enough, you will find that measure. Or in other words, if you look down far enough at almost any point in the support of this measure, you will see a picture of the Mona Lisa or any picture that you want. So while we know that there exist tangent measures at almost every point, we'll actually often use the following criterion for the existence of tangent measures that will actually be a little bit stronger, in the sense that it will say a little bit more about what kinds of tangent measures exist. So suppose we have a radon measure and a point A in Euclidean space, then the following conditions are equivalent. So firstly, for any sequence of radii going to 0, we can pass to a subsequence such that the sequence of blow-up measures TARI, push forward mu, divided by the measure of the ball center at A of radius RI, converges weakly to a non-zero tangent measure. Okay? So this holding for all sequences of radii going to 0 at a point A, this is equivalent to the lim supremum of the measure of BAR, the BA2R, divided by the measure of BAR, or in other words, the ratio of the measure of a ball to its double, that this lim sup is finite as R goes to 0. So if either of these two things are true, then what we know in addition is that the set of tangent measures of mu at the point A contains 0 in their support, and moreover, any tangent measure can be expressed as a limit of the following form. So recall that the set of tangent measures originally was defined as the set of all limits of the form some constant ci times TARI push forward mu. So what this lemma is saying is that up to a constant multiple c, we can actually pick this number ci to be 1 divided by the mass of the ball. And in this way, we recover all tangent measures. I won't prove the whole theorem here, and I'll leave some of the details for you to verify on your own, but I will show the details of 2 implies 1. So that is, if the ratios of the measures of each ball centered at A and its double remain bounded as R goes to 0, then any sequence of blowups of the following form will converge weakly to a tangent measure after passing to a subsequence. So suppose that the lim supremum, the measure of the doubles at the point A, is strictly less than some finite number c. So this implies that there exists some number r0 bigger than 0, such that for r less than r0, we have that the measure of the ball center at A of radius 2r divided by the measure of the ball center at A of radius r is strictly less than c. Okay, so now let's let rj be some arbitrary sequence decreasing to 0, and let's let mu j be the sequence of measures TARJ push forward mu divided by the measure of the ball center A of radius rj. Now observe that if we let boldface B denote the unit ball, then we have that the measure of the unit ball, the mu j measure of the unit ball is equal to 1 according to this definition. Okay, now also observe that if we look at mu j of a ball B, so say we look at twice some number r times the unit ball divided by mu j of r times the unit ball. Okay, well, by definition, this is going to equal the mu measure of the ball center at A of radius 2r rj divided by the measure of the ball center at A of radius r rj. And this is going to be less than the constant c so long as, okay, so this will hold so long as rj is less than this number r0, which will certainly be the case for large enough j. So thus, for any integer k and for any integer j large enough, we have that the mu j measure of 2 to the k times the unit ball. Okay, this is the same thing as this product, this telescoping product, I equals 0, k minus 1, of mu j, 2 to the I plus 1 times the unit ball, divided by mu j of 2 to the I times the unit ball. Okay, and notice that when I is equal to 0, in the denominator here we have mu j of the unit ball, which we recall is equal to 1. So that's why this product ends up telescoping and equaling this value. Okay, and then by this inequality right here, we know that for j large enough, the ratio of the measures of this ball with the measure of its double is going to be at most c. And since there are k many terms in this product, this is less than c to the k. So now what we've shown is that the measure mu j is uniformly bounded on compact sets. So this implies mu j is bounded on compact sets. And so from the week 1 review of measure theory, this implies that there exists a subsequence such that mu j converges weakly to some measure nu inside our set of tangent measures. We now record the following useful lemma that says that any two measures that are mutually absolutely continuous will have the same tangent measures. So suppose we have a radon measure mu and another measure lambda that is absolutely continuous with respect to mu. And in particular, its density is equal to some locally integrable function f. Now suppose we have a point A in Euclidean space so that the value of f at A is positive and finite, and it's also a Lebesgue density point for the function f. Then the following holds. Firstly, if we have a sequence of blowups applied to a measure mu converging weakly to a tangent measure of mu at A called lambda, then the same sequence of blowups applied to lambda converge to f of A times nu. So in particular, these blowups will also converge to a tangent measure of lambda at A. Conversely, if we have a sequence of blowups of lambda converging to a tangent measure of lambda at A, denoted nu, then the same sequence of blowups applied to mu will converge to f of A to the minus 1 times nu, and in particular to a tangent measure of mu at A. So in particular, we have that the tangent measures of mu at the point A agree with the tangent measures of lambda at the point A. The proof of this lemma is similar to how we showed that the tangent measure of Lebesgue measure restricted to a set was almost always just a multiple of Lebesgue measure.